degrees.
So getting an okay on your homework, does that mean you get 100% for that check?
So, if you get your homework back and it says okay or has a check mark, you got 100% on the homework. If it says correct mistakes, correct, then you have basically half credit, 50% on the homework. And if it says redo or no credit, then obviously you had no credit on that homework. I don't think that's happened too often yet. Anybody not get the handout from last? I think this was maybe even a couple times ago. Yeah.
So is it safe to say we had two tests? Is the final cumulative?
He gave you 7 and 11?
Yes. And you find an A. So I found...
Oh, he didn't give you a score of 170?
No, you find out the high part of the score and you leave it in the square root.
All right. So we're in section 5.3, really. We've made it through 6162, 5152, in 5.3. That's where we are. It's not easy to keep track of these two trig chapters because it just made more sense to me to bounce because we have the same idea just with radians and degrees. I don't want to repeat myself, so what the hell? Any questions from homework so far?
I have a question. For the final, is it cumulative?
Oh, yeah. The final is definitely cumulative. I can't say that word either. It's okay. Cumulative. It's the judicial system. Those words that make you sound drunk. Huh? I'm not kidding. I'm kidding about the way it sounds. I'm not kidding about it being cumulative. I did it. Worcestershire sauce. Worcestershire. All right, so you're the go-to person for that. Let's see. And it's going to be...
2 pi r?
Yeah. Any other questions, homework, or procedural questions? Procedural. Yeah, it is. Yeah. That sounds more like John Wayne. John Wayne and James Bond. 6-2. All right, guys. I got a question from 6-2. Number which one? 24. Cool, man. So it says sketch a triangle that has acute angle theta and find the other 5 ratios of theta. So recalling that trig functions really only directly relate to 90-degree triangles, we'll find out later that they don't. You can use them in other situations, but if I want to draw something from a given statement like this, I pretty much have to draw a right triangle that this directly represents. Because the definition of cosecant is based off the ratio of the sides of that given right triangle. So that's what they really mean here, is draw this right triangle. Here's where theta is. Now, can somebody help me out? What's 13 and what's 12? What's cosecant in general? What over what? Cosecant is 1 over sine. Remember, C goes to S, S goes to C. Cosecant is 1 over sine. Sine is y to h, so cosecant is h to y. Or if you like SOHCAHTOA, you can figure out how that relates to the inverse trig if you like to. I'd much rather not. So where's 13? Yeah, it's
Cross
oh, smart ass. Now where's the 12? I like it. I like that. Everybody's doing this. I like it. So in order to find the other 5 trig functions, what do you need to be able to do that?
You need no sine and cosine.
Yeah, I need that last one. You can't get one more. The most obvious one I can get would be sine. Sine theta has to be 12 over 13. Didn't even need the triangle for that. But what's this last side going to be?
Square root of
Maybe somebody help me out because I proved I can't apply that correctly.
it's the square root of well, sine squared plus equals 1. You have to use a 1 there.
I like this. Good pepper. So just to cut the theta is 5.
Sine squared.
Yeah, 25, yeah.
And some of you guys might know
Yeah,
that. You
5.
guys know the 3, 4, 5 triangle? 5, 12, 13. There's several more beyond that, but those 2 are the base ones.
But the bottom looks bigger. Why is the bottom?
It's not.
Because it's tilted towards you.
Oh.
Yeah. So imagine that. So now you can fill out the rest of these. What would the, is everybody cool so far?
Yeah.
Yes, ma'am.
How do you know that theta is on that side? Is that just given? How do you know theta is that angle?
I can draw this triangle whatever orientation I want to because they just said I can draw it. I'm going to put it there so that all my ratios are related the way I want them to be. I want sine to be related to the y piece, so forth. If you want to do this based off of SOHCAHTOA, your triangle can actually be in other rotations. But so what would, for example, what would cosine be?
Cosine would be
5 over
5
Beautiful. Cosine is the x piece, 5 out of
over
13.
13.
Tangent theta.
13 over.
Careful. Careful.
Tangent.
12 over 5, right? Tangent is y over x. Tangent very often is considered, and actually you'll find out in calculus how it is more directly related to a slope. What's slope? The most basic definition of slope, rise over run, it's y's over x's, right? And what's tangent? Y over x. So tangent is very often considered, and it comes out of some procedures, it actually comes out to be the slope of something. You'll see when you get to calculus. So tangent, we got those 3. We've already got cosecant, that's cool. What's secant going to be?
13 over 5.
Yeah, 13 over 5. And then cotangent?
5 over 5.
5 over 2.
Yay.
Cool. That's the kind of basic problem that needs to become really something you're comfortable with. Right? That should be a very easy problem very soon. Maybe not quite yet. Okay, cool. Yes, sir.
Are those numbers the length of the sides?
Exactly. These are the lengths of these sides. And actually, more generally, this describes a right triangle where the ratios of these sides reduces to this. So the actual triangle it came from could be a much larger or smaller, but this represents the ratios of the sides. Is that cool?
So is the teacher not to scale since the 12 is larger than?
Yeah, like I said, it's leaning out towards. Why? Because I didn't think ahead of time as to what was going to be where. So again, this triangle is just a visual anchor to put things in. It definitely does not need to be the scale. Yeah. Okay. Any other questions? Yeah.
Can you explain how you got 5?
Yes. It's a right triangle. What's got to work for the sides of a right triangle?
Something squared times something squared equals something else squared.
Pythagorean theorem. And then you just do the square root of 13 squared minus 12 squared. Yeah. Cool, cool. Have you ever noticed that if you write down the squares, as you write down the squares, the difference between the squares is actually just all the odd numbers. You ever notice that? How does that relate to what we're doing? Well, you could possibly think about what that means. The difference in the squares of 13 and 12 is 25, which itself is a square. So if the difference in between squares of any, like here's the 3, where am I at? The 16, 25, and 9. There's the 3, 4, 5 triangle. You guys see what I'm saying?
Ooh.
Neat. Oh. Cool. So that's why a lot of these will work. These are always going to be odd numbers. The odd numbers that happen to be perfect squares will end up related to a right triangle with nice whole number sides. Crazy. Crazy. It's also what human calculators use to do squares very quickly. They have like certain squares they memorize, and then they just add the next few odd numbers on to get the next square that they need. That's the little trick. If you want to waste synapses in your brain doing that, feel free. I have no desire to be a human calculator.
I've stopped generating synapses.
Okay. Any other questions from homework? Yeah. 6-1. 84, the one about the truck wheels.
Oh my.
This is page 442, number 84. So you have a truck with 48-inch diameter wheels is traveling at 50 miles an hour. Find the angular speed. In radians per minute. And then how many revolutions per minute. Okay, cool. So it kind of makes sense. Angular speed would be how quickly this thing rotates through angles. Linear speed, this is linear speed. This is angular speed would be radians per minute, or we can then convert it to revolutions per minute, which should sound familiar. RPMs, that kind of thing. Cool. So how do we start with this? I know it's a 48-inch diameter wheel. How does that relate to either one of these two? Because I personally might not do it in this order. If you get one, you can convert it to the other one. So let me help us out a little bit. If it's going 50 miles per hour, how long is this?
That's 2 pi.
2 pi r.
Yeah, 2 pi r, or even better, pi d, right? So the circumference of this is going to be 48 pi inches. You with me? Okay. And if you can convert that, now this, if anybody's taking chemistry, this should sound very familiar. You always want to try to make your units the same so then you can kind of make your chain so they can all cancel. If I want to get to revolutions per minute, for example, I want to know how many times does the thing go through a complete revolution every minute, and that's more directly related to this. Because one revolution is that long, and it goes 50 miles per hour. So let's kind of break this down a little bit. So I want revolutions per minute. So I can do one of two things. I can either convert 50 miles into inches,
Yeah.
or I can convert 48 pi inches into miles. Normally we like to take and break it up so that I don't get some crazy small number. You guys semi with me so far? Sort of, okay. All right, sort of. So if I have 50 miles per hour, and let's do that same, let's change this into inches per minute. So what could I do to get there?
Well, you have to.
I mean, know how many feet in a mile, for example.
5,280.
I like it, 5,280. So where can I put that? Where would I put 5,280 miles?
Underneath.
On the bottom. And up here I'd put the
1 mile.
One.
Oh, what did I
No,
do?
it's on the opposite, yeah.
I'm doing the number and then I put the miles down there and the feet up here, so
Yeah.
5,280 feet per
So
mile.
1 mile.
Thank you. So the miles go away?
Yeah.
And then how do I go from feet to inches? I got 1 foot, 12 inches. Cool. So now I'm in inches per hour. Right. So this is really a kind of problem where you're not going to find a recipe for how to do a problem like this. You're just going to have to take it step by step and see how to get something to match. I'm trying to work towards the middle here. I got miles per hour. I'm trying to go to something per minute. So it kind of makes sense to make that go to something per minute. I've got inches involved with my wheels. Let me make this into inches then so they match. So what's that last step I can do here?
16.
Minutes.
Yeah, 1 hour is how many minutes?
60.
60 minutes. It's awesome. So now I do 50 times 5,280 times 12 divided by 60. So it should come out to be 52800.
Yeah, because 60 and 12 is 5.
Yeah, that's 1/5 of 50 is 10 times that adds a 0 on the end. Sweet. And then what's the units going to be?
Inches
Inches
per
per
Inches
minute.
per minute. So my car is traveling at something we would never normally say. 52,800 minutes, inches per minute. That's the equivalent of 50 miles an hour. So next time I'm going 50 miles an hour, just remember that.
Tell the call.
How fast are you going? 50
Every revolution,
inches per minute.
is 48 pi inches.
Yeah.
So I want to go from 52,800 inches per minute. I want to go to revolutions per minute. See, I would do this. It always happened, especially in physics. I'd get part B and then I'd go back and get part A from that. I'm like, why did they ask in that order? Anyway, how would I convert that over to revolutions per minute? I have a conversion now between inches and revolutions.
1 revolution.
One
Yeah.
revolution.
1 revolution
is 48 pi
for this wheel at this rate is 48 pi.
inches.
I mean, for that wheel, it's 48 pi inches. Oop, not that. Thanks. So that's going to be revolutions per minute.
Over pi minutes.
What's it come up to?
1100 over pi.
I like it. 1100 over pi. It's not a bad way to keep it.
Revolutions per minute.
Over pi minutes.
Over 5 minutes.
Now, how do you get part, well, I say part 1 here. How do you get that from what we have so far? So this is part 2.
1100 revolutions
Well, we
per
know
pi
that
minute.
1 revolution is 2 pi radians.
I love it. 1 revolution is 2 pi radians. I don't care what kind of freaking wheels you got, right? So then I can take my 1100 revolutions per pi minutes. 1 revolution is 2 pi radians. Let me just stop right there. Does that in itself make sense? If I go through 1 revolution, how many radians have I gone through? How far is that from 0 to 2 pi?
2200.
So no matter what, 1 revolution of a circle, or whatever circular thing it is going to be 2 pi radians.
Per minute. Oh.
So I know how many revolutions per minute I'm going, so then I just need to convert revolutions to radians, and I'm good to go.
Do you decrease and radius count here?
Say again?
Do you decrease or you know how chapter 6 is degrees and then radians?
Chapter 5 is radians, yeah?
So I probably on degree is it affecting?
No. Shouldn't be. So now here the pi cancels out. That's kind of nice. So I get 2,200 radians per minute.
So we should tell the police officer that's how fast we're going.
Yes.
In problems like these, do you want us to not do like real numbers? You want us to keep the pi in there? That's how you like the answer?
Well, no, I kept the pi in there. To tell you honestly, I kept the pi in there because I knew it was going to cancel out here if I did. In general, we don't know that, so you can certainly just make this. What is this as a decimal?
350.14.
Divided by 4.
350.14.
250.14.
And if you use that number here, you'd get nearly 2,200. Yeah, that's fine. I just did that because I knew it was going to go away. Yeah. Is that problem easy? Maybe not. It's not, the reason this problem is not easy is because it's not prescribed. It's not a problem that's, oh, it's that kind of problem. No, it's actually something you got to sit down and think about and think, okay, how do I do this? I don't have any examples to do this on. I just have to convert and convert and convert. This is a practice in conversion. Cool. And more importantly, for some of you guys, that's a done problem. So, it's done. There's a given. Okay. Yeah.
Is that radians or revolutions?
This will be radians. The angular speed of radians per minute. Because the revolutions canceled. Sounds like some weird political science class. Any other questions from the homework? All right. If there's no other questions from the homework, we are going to get back into section 5.3.
You can measure the wheels on your car and figure that out there in the car. I mean, it'd be so easy. All you need is a tape measure and a calculator. That's cool. Very practical.
The motivation to do it.
Yeah.
Motivation. Yes.
I'm just gonna go measure
That's a tire
tires.
to come by.
Go measure tires in the parking lot right after this class.
Hey man, do you know how many radians per minute your car goes?
Well, would you measure your wheel?
Yeah.
Or would you measure your tire?
Tire, whatever contacts the ground.
Exactly.
But really,
At full.
Out to where context of ground. That's what's important.
does it get bigger as you
Maybe unless you
drive?
wanted to determine.
So if you have your tricked out car and you've got these monster tires on there, you've had to pull your body chassis up away from it, then you'd have to, yeah, exactly.
If it gets hot outside, your tires get bigger.
All right, so let's do a reminder from way back when. You guys help me out. If I have given some function f of x, if I do this, how will it shift? Let's say that this is going to be always a positive number.
Shift C to the left.
Yeah, so if this would shift
Left.
C to the left, what would this do here?
Down.
Yeah, shifts down C units. Cool. What would this do here? Now, this is an interesting question because it depends on what C is itself.
Like that.
It's going to alter kind of the slope, how quickly it rises or falls, right? It's either going to make it skinny or fat. If C is less than 1, it's going to make it rise slower, so it's going to be fat. I'm thinking about parabola now, but this is in general true. And so it's going to make it rise slower. If C is greater than 1, rise quicker. So, did I say anything about the specific function that I'm using here? No, so obviously these things are true no matter what function we use. So if I have this, what would that do to that picture? Yeah. So we just talked about last time about what do these look by themselves? What do these trig functions look like if you graph them by themselves? Now, of course, immediately we're going to start playing with that. We're going to start picking it up, moving it around, squishing it. This is just going to pick up, what's the main things I could do with sine? What's kind of like the main 4 anchor points that I use? 0? And where is sine and pi over 4? Not pi over 4. Pi over 2, pi. 3 pi over 2, 2 pi. you can always start with those 4 base ones. Now if I graph the base function, which means the dotted line one that I do, that means I haven't shifted anything at all. At 0, what sign?
0.
Beautiful, because there's no y piece yet. At pi over 2, it's
1.
1, 0,
Negative 1.
negative 1,
0.
0. So it goes. Okay, cool. So now the shifted one, what's this shift going to do to my picture? 5 over 4 to the right, right? So it's going to move. So this is going to move here. This is going to be pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Okay, Jeff, we get the end of it. You guys kind of with me? In fact, I'm going to make a slightly better way to do this problem, but I want to kind of associate it with what we did before. What did we do before? We had the function, and then we actually just picked it up and moved it over. I'm going to show you some more direct ways to do trig functions. So now my function looks like this. That's going to move here. Oh, yeah. Oh, what will it do? That's going to move here. And then, of course, I need one more here. So now my graph.
This is 2 pi over 2, right?
Is that cool?
1/2 pi over 2.
So that's pretty basic. I mean, now I could do all this other stuff to it. Let's do one more thing before I show us sort of the shortcut way to do this. If I had So just looking at this from the standpoint of a function, when I put something inside like this, who remembers what that does? Normally when it's in with the x, it does the opposite of what it looks like it should do. So in the x direction, and actually it takes all my inputs and makes them... So now since these things look like springs, this idea of compression makes even more sense. It's going to end up compressing my cosine. Right? Okay. So actually, let's take this next step then. Let's actually go ahead and take this next step. The period for cosine is normally what?
2 pi.
2 pi. I love it. For tangent, it's pi. I love it. That's what that little cubish thing fits into, right? It fits negative pi over 2 pi, it's pi. Cosine and sine are both 2 pi. That's how long it takes them to do their thing. Okay, cool, cool, cool. So here's the cool thing about if I put a number inside here. We just said that it should shrink that down. So what ends up happening is I take the period of whatever trig function I'm talking about divided by this coefficient. So in this case, 2 pi divided by 2, pi. So now the period is pi. Has it shifted left or right at all?
No.
No, so it's still going to start at 0, right? It's going to be at the highest point there and go from there since it's cosine. And this 1/2, all that's really going to do, the cool thing about whatever changes this is it's going to be easy to take care of. Cosine normally goes from negative 1 to 1. Now it's going to go from negative 1/2 to 1/2. Ooh, right? It's actually not going to change my picture at all. Because I'm just going to, when I do it, I'm just going to zoom in and make that 1/2 negative 1/2. Yes, ma'am?
So in both cases, it's just the opposite of amplification.
That is
Yeah, this is actually exactly what it looks like. It actually does make it go half. But whenever it's in with the x, like if it was x minus pi, you would actually make it move to the right pi. It's always the opposite of what it looks like it's going to do. All right, so that kind of makes sense. That ends up, because all my inputs can now be half as big, because the first thing this does is doubles them. So that's why they can all step in halfway. Now here's the next cool thing we can do. especially because it hasn't moved left or right at all. Normally I use 0, pi over 2 pi, so forth. How far is it going to go out now to complete a period?
To pi.
Let's complete a cycle that goes out to pi. So now I can break this up still into the 4 parts. This is crucial. You have to know what it looks like through those 4 anchor points. So now if I smush it or if I elongate it, I just go out to where it ends and then cut that up into 4 parts. And then just draw in the picture. It's not nearly as difficult as it would seem it was going to be to move these things around. So what is this going to be now? Pi over 2. So this has to be pi over 4.
3 pi over 4.
3 pi over 4. I love it. So now it's going to look exactly the same as it always does, but you just basically relabeled the points to fit what's happened to this poor dude. So now at 0, where does it start off? Careful. 1/2. It's going to be maximal at 0, as long as I haven't shifted left or right. And then it's going to go, what's that happening here? Goes through 0, negative, the minimum, so max, 0, min, 0, max. That's basically what cosine does. So now you're just drawing a little bit past there, and a little bit past there. Not too bad. So to incorporate everything at once. The thing I haven't done yet is to lift this thing up and move it up and down, but that's just the last thing I would do. If I put on here +2, that's I just take the whole thing and move it up 2. Not a big deal, right? So I'm not even too worried about that. Yeah?
Is there like a generic formula for that? Like
There is. And I even have a handout for it. Here's the idea with sine and cosine. Let's see. Use omega or do they use omega? They use B plane. Put that in the right place. Have that out there. I'm not going to worry about that part. That's the easy part. I always think about physics. We do this in physics all the time because in physics you talk about the frequency of a wave. If you push it, then you increase the frequency. Any of you deal with sound or anything at all, then that sounds familiar. So here, the period is going to always be, for sine or cosine, it could be either one. The period is going to be 2 pi over k. The translation, the linear translation, if I move it left or right, that's called a phase shift. And in this case, it's just going to be b units right or left, depending on whatever sign b is. You with me so far? Okay? And the really nice thing is, yeah, of course. I'm just looking between my handout and the book. And of course they did that mine a little bit differently. It's too bad for me. Oh well, too bad for me. Oh, and the amplitude, that's a little new word, but that should make sense. It's how far up and down it goes from 0. Normally it goes up and down 1. This is going to go up and down 8. Cool. So this is too bad. Let me confuse the issue just a little bit. Let me give you this.
Apparently there's almost 10 that are living in this mission. Jay-Z now has a half
What's with my balls? So I did it the more general way, let's say. The way the book has it represented is not really a way you see too often. Very often, in fact, in the homework even, you'll have to factor out K to really see what the phase shift is. So to me, this way is a little bit misleading because it makes it seem like whatever that is, but it's going to be whatever it is after you factor K out. So let's do a specific example. We're not going to graph it. We're just going to identify the parts. And this whole thing works for tangent too. What's the only difference for tangent?
The period is different.
Here it'll be pi over k, exactly. Because it's originally pi, it's going to be cut by k, factor of k. So if I have so the first thing you need to do, and I think that my handout makes it a little bit more obvious, what do you have to do first really here?
Plot that K.
Yeah, plot the k, the 3. So if I pull it out, what happens in there? 4 pi over 3. Okay, cool. So now identify the easy one. What's the amplitude? 4. What's the period going to be now?
3.
It normally is 2 pi. What do I have to divide by? Over 3. Because k is 3. Cool. So far, so good. What's the phase shift?
4 pi over 3 to the right.
Yeah, 4 pi over 3 to the right. I like it. Actually, I'm going to lie. I'm going to admit that I just lied. And I decided to go ahead and graph this. Because I want to show you how nice this is to do if you just focus on those 4 anchor points and where they're going to end up. So I know I'm going to start, my first point is going to start at 4 pi over 3. Because that 0 is where it normally started. It's been shifted to the right, 4 pi over 3. Does that make sense? I will claim. So I'm going to start at 4 pi over 3. Where will I end up? How do I figure out where I'm going to end? How long will it take for me to end? Like, that's what I always ask myself, Jeff. Yeah, a period. So what's the period? 2 pi over 3. So it's going to end 4 pi over 3 plus 2 pi over 3. 6 pi over 3, which is...
6 pi over 6.
Oh no.
3.
2 over.
We made it. So it's going to end at 2 pi. And then all you have to do really is now break that part up. Break that up into the anchor points. Right? So now you can go, what's halfway in between those? Or you can think about if the period is 2 pi over 3, 1/4 of that. It's going to be, why am I doing that? Because if every step I take is going to be 1/4 the period. Are you guys with? There's a lot of different ways to do this, trust me. But to me, you can either just cut this in half, which means add and divide by 2, add and divide by 2. So what's right in the middle of these two? If you add these, what do you get? This will be 6 pi over 3 plus 4 pi over 3 is... So right in the middle should be half of that,
5 pi over
5 pi over 3. Makes sense. 4 pi over 3, 5 pi over 3, 6 pi over 3. You with me?
Yeah.
Bless you. Does this make sense so far? This is only one way to do this. All the ways to do this are just playing around with the freaking numbers. And that's what you need to be comfortable doing, just playing around with the numbers. I know you're playing around with numbers in the context of graphing a trig function, which you just learned, but I don't care. This is just playing around with numbers that I have to break up into 4 parts. A lot of different ways to do that. So I go halfway again. This one shouldn't be too bad. Maybe it will be. I don't know. Make it 8 pi over 6, 10 pi over 6, so this should be 9 pi over 6, which is 3 pi over 2.
6 pi.
So 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. So that's what I was saying earlier. If I take the period and take 1/4 of it, why would I do that? Because every step I want to take is 1/4 of the period with me. Cut that period in 4 parts. That's my 4 anchor points. 1/4 of the period will be pi over 6. So add pi over 6, add pi over 6. To me, that's the quicker way to do that, really. You guys semi with me? What the hell am I doing all this for? Because if I can figure out where my 4 anchor points end up, I just graph the freaking sine or cosine or whatever function is on top of that, and I'm done. Yes?
Can you go backward and show how she did it again?
All right, so let's see. Let's recap. Amplitude nuts, right? So I just got to, when I label my horizontal axis, I just have to, my vertical axis, I just have to put 4s on there instead of 1s. Period, it's always going to be what the period normally is for whatever trig function I have, divided by that number that shows up here. So in this case, sine 2 pi divided by 3. Cool. Phase shift, I can see it now that I took the 3 out. I can see how the x is being moved to the right by this much, which told me where I'm going to start. I know how long it takes me to end, so then I know where I'm going to end. Right, so that period tells me how much past this until I get to the end of that cycle. Right? Of course, the actual function itself goes forever. Now from there's a lot of different ways to get the numbers I got up there. To me, the most direct way is this way. Take 1/4 of the period and then just start adding it on from one end. What's the check? Make sure you actually end up where you know you're supposed to end up. Right? If you don't, then something went freaky somewhere. Yes, ma'am.
So what did you say about the quarter? You find a quarter of the total distance?
Yeah, because if I know this is the period, and I know that my anchor points are all, I have one, basically 1, 2, 3, 5. I've cut this into 4 parts, really, right? Then I want to go 1/4 of the way to get to that anchor point, another 1/4 of the way. So if I know what 1/4 of the way is, it makes it very easy to do this. So from the beginning, instead of doing all this cut it in half, I could have done, what's 4 pi over 3 plus pi over 6? 8 pi over 6 plus pi over 6 is 9 pi over 6, which is 3 pi over 2. Add another pi over 6, add another pi over 6. Much more direct then. If you don't like that way, sweet, I love it. Do it the other way. Cut it in half again, cut the other ones in half. You got it that way too. Now what do here I got to put
4.
or negative 1. And then sine at the start starts where?
0.
0. And then the next anchor point, it's at the max, 0, min, 0, and keep going after that. So it's going to go. Is that semi-decent?
And if it were cosine, it would have started at the 4.
Exactly. The only difference was right here, cosine would have been there.
And then going down.
0, yeah, exactly. So it really focuses your attention on those 4 anchor points. Where do they end up? And then just draw the shape it. You're good to go. What I get from people very often is just, and there's no scale. There's no anything. It's obviously the most important part really is that where do those points end up? So does that follow from this, hopefully? Do you guys see how, hopefully everything I just said kind of is represented here? I'm trying to help you through this section. I gave you two ways to do this, and they're both actually the same way. The begin and end cycle right here in the middle. You don't have to look at that if you like the way we did it up here. Either way, that makes more sense. So, let me give you one to try on your own. You guys do this one here. I'll give you a little hint before you drive yourself insane. When you go to draw a picture, your scale should have no pies in it. No, I do that all for sine and cosine. The sine and cosine I want to break up into those 4 anchor points. So it's normally pi over 2 pi. And that'll tell me how far to go to get to the next anchor point. If I know where I start, I'm going to go 1/4 the period to the next one, 1/4 the period to the next one. Yeah. Yeah.
Take it backwards, don't I?
Yeah, that's why it starts like that. Because this would be a 0. So the 0 goes like that. Yeah, it's 1.5.
Oh wait, these are half. This is like 1/2, right?
No, it's not better.
There's no pies here at all.
Because of what you step by step.
Yeah, pretty sad.
If I were to try to figure this stuff out,
But my period's still 2 pi.
No, your part is 2.
I'm sure I can do a lot of things. It would take a lot more learning. I'm sure I can figure out things once or two. Probably not the first day. You know?
My period is 2 pi over k.
So like a lot of people,
It's, yeah, and K is pi.
I'm like,
Oh, crud.
this is concept of like, yeah, it's basically works, but it's like, I'm just thinking about like, this guy next to you, who's listening to this class, he's gonna come back on Monday and be like, what?
Yeah.
Yeah, that's what I'm saying.
I don't like you said this.
Yeah,
so funny.
Come back. Yeah. Every time you come back and you feel like, you're so lost, I should not have seen the class. So it shifts to the left, right? Well, your period is 2. Okay, it comes
So,
out to be
because my period is 2, it only goes to here.
So now it's going to teach you already have that now. Okay? And whenever I set it at 4 anchor points, so you divide 2 by 4, and this you get your halves. Now here's the other from the start. So you get your halves. So there's your 4 anchor points. That's a half to the left. For that side to 0, shift half to the left. That's a half. And then my regular is the start. Okay. Now on a regular basis, this is how your cosine will always work.
Except you want to dot down that too. That's
Oh,
why.
oops. Yeah, but that's meant to be there. I meant to do that.
Cosine starts. This is my, since I moved to left, it's not easier.
Oh, God, it's so fine. It's here, it's gotta go here.
Yep, exactly.
Next one goes right.
Yeah, and for every 4th increment, so in this case, every half, you go max, middle, low max, middle, max.
So this one here,
Like that. Except for my negative 2 is like way down there. My 2's there. It's fine. That's what I meant.
But still, it doesn't matter. Everyone has to do their scalars, right? Your scale will be off, but as long as you're doing it.
Yep. And it's easier to understand with this when there's no pies involved.
Why does cosine only do? It's supposed to be kind of like a this.
Exactly. It's just a longer sine
You
wave,
know that the period's going to go max,
and the amplitude is different.
middle. Once you have that, then you can go.
See, it's the sine wave, but it's this kind of sine wave.
I'll take whatever's.
So
Then you can see actually shift.
Yeah.
this,
But it's supposed to kind of go.
I think it'd be better like the.
Let me just go and everything.
It's gotta come out. So that'll make that 1/2.
It's supposed to kind of go like this.
By normally divided by whatever you
Like that.
Yep, 2 divided by.
Kind of like that. Because it kind of goes.
I'm gonna sit down. I gotta sit down this because I can't do this.
But it would look different if it were on a real scale, 1-to-1. This is not a 1-to-1 scale, it's 1/2. And
All right.
Silly goose. Why would you think anything else?
So what's the amplitude? 2. I'm not laughing at you. Nothing weird. What's the period? 2. Because the first thing I need to do,
take out the pies.
take out whatever that coefficient of x is. Take it out. Period will be 2 pi divided by whatever ends up there. And then now I can also see the phase shift.
Half to the left.
Apple pie.
Yeah, so it's 1/2 to the left. Or you can just say negative 1/2. What the hell? And then you say, so it's going to start where?
At negative 1/2.
Negative 1/2. It's going to end how much past that?
2 past that.
2 past that.
Half past.
Okay. This one.
The phase shift one more time, please. The phase shift one.
Oh, phase shift? It's really just, it's the technical term. When we're talking about trig functions and they move left to right, we call it the phase shift. It's just new terminology. How much is that going to shift? 1/2 to the left, right? 1/2 to the left, correct? So that's why it's just given, that's the name we give it when we're talking about trig functions. It's the phase shift. Cool. All right, so when you graph this thing, starts at negative 1/2. And this is cosine. This is going to be 2, negative 2. scale is awesome, Jack.
That's an awesome scale.
Starts at -1/2. Cosine starts maximal. Now the only difference, I almost put a -2 in there, but I don't want to do that to you. But the only thing that would do is if it starts at the top, then now it's going to start at the bottom. Right? Not a big deal. So if it's a negative in front of here,
Flip it.
that just flips it. We know that's what that does. This didn't, so it doesn't. Maximal 0. Minimal 0. Maximal. Cool. Yes?
How did you find those 4 anchor points?
In this instance, what I did was I knew I had to go back a half, so I knew that's where I'm going to start. I normally start at 0, so now I'm going to start at -1/2. The period is 2, so it should end 2 later. So it should end at 1.5. I didn't really do any math for that because it pretty much fell into it. But if you want to do it the way we did before, 1/4 of 2 is 1/2, so every step I take is 1/2. 1/4 the period will be how many steps between each anchor point. Does that make sense? That's how I can build that. That always works for cosine and sine. Just because the way that I personally do this, and most teachers kind of do it the same way, I use those 4 anchor points. So it's going to naturally break the length of a cycle up into 4 parts. 4 equal parts. So if I do 1/4 of the period, that tells me how far to get from the first one to the second one to the third one. And I know where I'm supposed to end, which is a nice check and balance, right? Okay? Yes, ma'am?
So if it was tangent, it's just.
Yeah, I was about to say, let's try a tangent one out. And then we'll get into the inverse. Not the inverse.
Oh boy.
The reciprocal trig functions.
Did you find that then? Where it's supposed to end?
Where it starts, plus the period. Because the period is defined to be how long after it starts until it's back to that same position again.
I think I was just confused because you used 2 last time.
You have to use whatever the period is now for that function. Good.
But why does cosine start up there and sine starts at 0? Sine starts at 0?
Because the unit circle tells us to.
Because if cosine likes x and sine likes y, at 0 degrees, I'm all x. I'm no y. You with me? If cosine represents the amount of x I've got, it really does. It represents the percentage of x that I've got. And sine represents the percentage of y that I've got. Well, if I'm at 0 degrees, I ain't got no y. Just to completely screw grammar up. You with me? So if I'm all x, that means cosine is going to be 1. It's 100% cosine. It's 100% x. 0% y. That's why sine is 0 there. So graphically, that's what's going to happen. That's how it's going to start. Yeah.
The cosine start on the top when we're graphing and the sine start from the 0.
Yes.
Yeah.
Reference everything I just said. Okay. So let's try out. Yes. Real quick, since I've got this picture up here, if I wanted to do, what's the reciprocal function that goes with this? Secant. So if I wanted to do 2 secant, here's a really cool thing. If I want to do 2 secant, every point will be the reciprocal of the point that's on the graph right now. So for example, where is my secant going to go to infinity? Where's there going to be vertical asymptotes? Wherever cosine is what value? If secant is 1 over cosine, all the places where cosine is 0 will be where my secant graph has vertical asymptotes. So that would be a vertical asymptote. Now, for example, what's 1 divided by, I'm sorry, at 1/2, the output of this is -2. You with me? And I'm kind of skipping a few steps, that's all right. for, I don't know if I really want to get ahead of myself. If I have my normal cosine function